So the order of magnitude that CDR as a market needs to achieve is hard to perceive and comprehend. We're on a journey to make a planetary scale impact and cool down a planet. And this is not something that any industry had done before.
Hi everyone, welcome to the Climate Confident Podcast. My name is Tom Raftery, and with me on the show today, I've got my special guest, Ori. Ori, welcome to the podcast. Would you like to introduce yourself?
Hi, my name is Ori Shaashua. I'm the co-founder and chief commercial officer here at Gigablue. My background spans through a range of companies that I've built. This is my fifth company, and I tend to focus on areas of deep tech and impact, and leveraged AI in health, mobility, transportation, energy. And 3 years ago, decided to take my skills and expertise to climate.
Great. And for people who are unfamiliar, Ori, what is Gigablue?
So Gigablue is a marine carbon dioxide removal company. We're the world's largest supplier in the space. And Gigablue is leveraging a methodology called MCFS that basically exports CO2 from the surface of the ocean to long-term sequestration in the deep ocean, in the sediment of the ocean. And we are operating out of the open ocean, 300 kilometers off the shore of Dunedin, New Zealand. And we're based in New York.
Let's start with the 30,000 foot view. Why is removing, let's say, 10 gigatons of CO2 per year by 2050 such a tall order, and where do the oceans fit into that challenge?
So the order of magnitude that CDR as a market needs to achieve is hard to perceive and comprehend. We're on a journey to make a planetary scale impact and cool down a planet. And this is not something that any industry had done before. And over the course of the evolution of humanity, over the course of the Industrial Revolution, it took us decades over decades to make an impact on climate. Imagine how many years and decades it took us to get the planet to where it is today.
Mm-hmm.
And we're trying to recover and basically fix the damage, so to say, that was done through geoengineering that took us many decades. And we are trying to fix it within just 2 or 3 decades. It's a huge effort. And the level of intensity that needs to be applied to make that happen needs to be just at the minimum equivalent to the effort that we had invested emitting carbon to the atmosphere.
And when most people think of decarbonization or carbon capture, they think typically of trees rather than oceans. So why do you think oceans are do you think they're better than planting forests? And if so, why?
So it's not my opinion. The ocean is the world's largest carbon sink. The ocean captures 50 to 60 gigatons of carbon each and every year. Even I wasn't aware of that in my previous AI life, but so it is, and so it has been for the last 3.5 billion years. There is a natural process that captures carbon in the ocean, and the ocean has a massive potential to sequester carbon for thousands of years. So the ocean is not only representing a massive scale potential for carbon sequestration and removal, also from a durability perspective, the ocean is as good as it gets.
Can you walk us through the marine carbon fixation and sequestration technology that you have in Gigablue in plain English?
Yeah, sure. MCFS is basically the controlled export of CO2 from the surface of the ocean to the sediment of the ocean. Once CO2 reaches the sediment of the ocean, it gets sequestered for anywhere from hundreds to thousands or even 10,000 years or more, depending on where it lands. And if CO2 reaches the right conditions, it can really be sequestered for thousands of years. Nature does capture 50 to 60 gigatons of CO2 every single year based on tiny microscopic algae called phytoplankton, which is the world's most efficient machine of carbon capture. And phytoplankton captures that amount, but only 1% of the amount that gets captured actually reaches from the surface of the ocean to the sediment for long-term sequestration. So there is a
Okay.
huge potential and a gap. And the MCFS was developed to bridge that gap. If you really want to oversimplify things, we are an elevator for CO2. And we make sure that the CO2 that is captured on the surface of the ocean also makes the full journey in a measurable, controlled, traceable way to the sediment of the ocean, to a place in the sediment depth and chemistry that allows for very long-term sequestration of
Okay.
1,000 years or more.
Okay. We can understand trees because a tree grows from a sapling to a large tree, and a significant amount of that is wood, which is carbon. Talk to me about phytoplankton. How are they sequestering carbon? Because obviously they don't grow into trees. What's the mechanism there?
I will start by just saying that phytoplankton is a tiny tree, right? We are farming microscopic trees on the surface of the ocean. We grow them inside a substrate that we have developed, and they develop and form a colony inside the substrate. And if you kind of zoom in, you will see a microscopic forest that photosynthesizes just like a tree, which is the most natural way to capture carbon. And then we just make sure that this colony of phytoplankton actually makes it all the way down to the deep ocean, to the sediment, focusing on areas that contain calcium carbonate, which further increases the durability of the sequestration. But in essence, if you can understand how trees work, you can definitely understand how phytoplankton works. It's just a tiny tree.
Okay. And how do you make sure that 99% more drops down and sediments? Because you said in the normal run of events, only 1% sinks to the bottom and is sequestered. So how are you adding that extra 99% to make sure it goes down?
So MCFS is happening and occurring within a controlled environment within the substrate rather than in the water. And the moment that you are growing additional phytoplankton, not taking the phytoplankton that grows in the water and depleting nature from its own phytoplankton, but you're growing your own inside a tiny substrate in which a mechanism controls sinking and floating behavior, then you can also define the destiny of that phytoplankton colony. 10 days after, 10 to 15 days, depending on the geography, after deployment, what we call the gravity core or the controlled sinking mechanism triggers. And the moment that it triggers, the density of the substrate becomes 2.5 times heavier than water. And it basically sinks like a stone. And it sinks using the power of gravity. And that is a big deal. Gravity is very cheap these days and very lean on energy. So if you compare this to other CDR, carbon dioxide removal methodologies, then there is typically some sort of high energy process involved in sequestration, whether it is pumping CO2 to an underwater or underground reservoir, or burial that involves heavy machinery, And that ends up increasing the cost of removal to the point that removal has been and still is in many other more expensive methodologies not financially sustainable for corporates. Affordability is limiting the impact on climate change. And the fact that in the case of MCFS, gravity is powering sequestration is a very big deal because it makes MCFS a viable, financially affordable way to reach net zero. And what we have seen in 2024 is how MCFS was very well adopted and received by the market. Gigablue signed 6-digit offtakes, way bigger than the large offtakes in marine CDR till then. The moment that corporates identified an opportunity to reach net zero in a way that is financially sustainable, the moment that they realize that they don't need to wait for the price point to go down and they can confidently transact today and form a long-term relationship with a CDR supplier, they did. So going back to the technology, and the fact that sequestration is based on gravity has a very big impact financially and also on the scale-up velocity of CDR as a market.
Speaking of scale up, what kind of numbers are we talking about in terms of carbon sequestered today, and what are you looking at scaling up to?
So we are operating seasonally.
Okay.
In the Southern Hemisphere, where our current project is, we are operating in Q4, Q1. And MCFS is a batch process that is lean on OpEx and CapEx. We don't need to basically build a site or a facility with a big investment. It also takes a couple of years to set up. And we don't need to operate that site for years in order to fulfill an offtake. We head out to sea, and we're planning to head out to sea this Q4. And over the course of the season, deploy one or more batches that fulfill multiple offtakes that have been signed over the course of the year. So it's a batch-based process. We have a scale-up plan for the upcoming few years that roughly is getting us to 100 kilotons in 26, 750 kiloton in 27, 4.5 million tons in 28, 9 million tons of capacity in 29. Based on looking at this curve, you can really see that the gigaton scale is actually truly achievable. An easy way, and more like a way that is more perceivable, even for me, to understand the scalability of MCFS, is if we think about it in vessels. It's hard to imagine 4.5 million tons, but it's much easier to imagine a bulk ship, a vessel, that carries 100,000 tons, that goes to the ocean and yields 1 million tons of removed carbon dioxide from the atmosphere. There is a mass ratio of 1 to 10. So for every ton of substrate, 10 tons of CO2 get sequestered. So if you kind of think at this process, and if you need to get it to a planetary scale, 1 million carbon credits is one vessel for 10 to 15 days. So if you want 4.5 million carbon credits in 2028, then it's either 5 vessels of 100,000 tons or 10 vessels of 50,000 tons. And if you imagine this process happening in parallel with 2 vessels, happening again and again, not once, so 10 days, and then back to shore, and then deploy again in a different field, and then back to shore. You can operate over the course of Q4, Q1, and really fulfill the demand that will be in the market at that stage and make a pretty big impact on climate.
Great that we're having an impact on the climate, but what about the impact on the ocean floor? Because if you're dropping 4.5 million tons of not just carbon, but phytoplankton carcasses, I guess, plus 450,000 tons of the substrate, whatever is in the substrate, and what is in the substrate, because is that going to be something that potentially harms the ocean floor as well? So talk to me about the impact of the substrate and the phytoplankton on the ocean floor.
So before we get into numbers, I will say that we've worked with NIWA in New Zealand and the Cochrane Institute to basically define limits and guardrails for everything that we do. And we've defined these limits far away from the potential capacity of the sediment. And I would also say that since this has never been done before, nature had done it, but we didn't, then we are also applying continuous monitoring before, during, and after deployments. And if you look at the charts generated during the experiment in the last deployment, we really proved that we are not making any meaningful impact on the water column, in the photic zone, or on the sediment. Now, with regards to zooming in to that, and let's get down to numbers, it's important to remember that nature does that at a massive scale. It has been doing that for 3.5 billion years. And the additional process that we add to the mix is a drop in the sea in comparison to what nature has been doing since forever.
Okay.
And so even though it sounds big, like in CDR numbers, it's like, oh my God, that's a lot. But when you look at what nature has been doing for so long, then we are not landing a meaningful amount of additional matter on the sediment. Specifically, even if we scale to the gigaton scale, there will be less than 2 grams of substrate on a square meter. That is very, very little, and definitely something that the ocean floor can safely handle.
Sure.
Another way to look at that number is it is less than 1% of the potential. So it's 0.07% of the potential. We are very far away from even getting close to the limits of and the potential of the sediment to our long-term sequestration. So the limits have not been set by us at Gigablue. They have been set by the National Institute of Water and Atmosphere and the Cochrane Institute. Those are third parties that are truly independent. They're not part of the voluntary carbon market like registries and verifiers. And they're the ones that will set the guardrails and the limits for the whole operation. And from a scale perspective, it's hard to encompass 70% of the surface of this planet, but the ocean is huge. It's not a physical site. You don't need to deploy in the same place again and again. What happens when we deploy is that the substrate floats for 10 days with the currents, and there is no concentrated biomass in any place that later sinks in one place and might create anoxic conditions. And so unlike biomass sinking and ocean iron fertilization, which is a capturing, not a sequestration methodology, that did cause an impact on the ecosystem, MCFS does not. And there is no concentrated biomass sinking anywhere or even floating anywhere because it all disperses across a very large area. And once it sinks, it's not sinking in a dense form in one location. If you look at on sequestration fields on the Gigablue map, you will see that they are bigger than New Zealand itself. There is a very big potential that we can uncover. And I really believe that the ocean is the way to go, not necessarily through MCFS. Many other ocean-based methodologies pose a huge potential that needs to be captured in order for us to really get to net zero. And even when we do get to net zero, there's a lot of cleanup work to do. There are 1,000 gigatons that we had already emitted over that we will need to clean up after we stop emitting, or at least offset what we emit every year.
And you're doing of New Zealand, as you said, around Dunedin. Is there a particular reason for that site, and therefore are you limited in where you can do it oceanographically?
The type of water that we deploy in is called HNLC, high nutrient low chlorophyll. In simple words, it's an ocean desert. The low chlorophyll means that phytoplankton not getting the ideal conditions for it to grow and thrive, even though there are the necessary nutrients available. There is a tiny missing gap of micronutrients that only exists inside the substrate and is not dispersed to the water. And therefore, the colony develops inside the substrate rather than the micronutrients being dispersed into the water and impacting the water chemistry and biology.
Right.
So this is essentially the type of water that we operate in, and a third of the ocean basically falls into that criteria. You would find these types of waters primarily on the southern ocean and the northern hemisphere, because micronutrients reach the ocean through dust storms, and there's not that much dust in the southern ocean or in the northern ocean. But if you look at the Atlantic, for example, it gets quite a lot availability and is therefore chlorophyll rich. So if phytoplankton is the base of the food chain and you've got an area that doesn't have phytoplankton, that means that you've got low biodiversity. If there's no phytoplankton, there's no zooplankton, then there's no zooplankton, there are no fish, etc., etc., etc. So, and micronutrients are a tiny gap that we need to bridge. And so that is essentially why HNLC is an ideal place to deploy. But New Zealand, it's not only about water chemistry and potential of the ocean to sequester carbon. New Zealand is very advanced on its net zero journey with an ETS that has been around for 9 years. And New Zealand is very environmentally cognizant, and the New Zealand EPA is very strict. And we thought that if we want to basically choose a site and deploy mCDR in the most responsible way, then we need to do that in a geography that is strict, that other environmental protection authorities look up to. And so New Zealand has been a great partner for us.
And what about the measurement and the verification of the amount of carbon that's being stored? Because, as you said, it's dispersed over a wide area and then sinks after 10 to 12 days. How do you know that that happens? Or how do the people you're selling the carbon credits to know that that happens?
Great question. So we are using a fleet of sensors, drones, ROVs, drifters, and acoustic measures to allow for full traceability. In fact, many terrestrial methods do not allow full traceability during their measurement, reporting, and verification frameworks, as the frameworks are in operation. Full traceability means that we actually see the journey from the photic zone to the deep ocean. And if you compare this to methodologies such as enhanced rock weathering, for example, you've got traceability until -3 to 8 meters below the ground. And then the rest of the journey of CO2 is based on models. In the case of MCFS, the MMRV framework doesn't only observe and monitor the journey through acoustic measures. And we also take samples, physical in situ samples in the deep ocean. So we don't only observe the journey, we also take physical ground truth samples. So we've got ground truth data from each and every deployment. And this built a lot of trust in MCFS and in the MRV framework of MCFS, because it is in many ways more reliable than other MCDR measurement methodologies that were primarily based on modeling, inferences, and statistics of some sort. That always was a limiting factor for MCDR to really get market maturity and adoption.
You're aiming for gigaton scale removal by around 2035. What would you say are the biggest technical or political hurdles that'll stop you getting there, or that could stop you getting there?
So the technical hurdles are, I would even say, a bit boring. Scaling up production to a planetary scale takes time. And the advantages are that we don't need any special facilities. We can produce the substrate in almost anywhere on Earth. We are already working with 5 different facilities in Europe, US, Asia. In the last deployment, we produced in New Zealand in a production line that has been developed specifically for this purpose. So once you are not dependent in building production facilities and you can use the existing ones, then it is scalable. The materials we use are natural materials. They are not something that is scarce or hard to obtain. Production is definitely something that we can scale, but it just takes time when you want to scale to this magnitude. I mean, if you kind of travel back in time and imagine how much time it took us humans to scale up the concrete industry. Today it's massive, right? 300, I think, million tons of concrete are produced every year, maybe more, I'm not sure.
Right.
But it's massive. So the concrete industry is massive today, but it took a while until we scaled it up. The technical limiting factor is going to be scaling up production. And the scale up curve that I described earlier is driven by the ability to scale up production. Politically, oh, that's a big one. 2025 has been an interesting year from a political standpoint, and I have a feeling that it's going to continue that way for a while. And while politics does have an impact on CDR, climate doesn't really care. We saw LA burning and natural disasters occurring in an increasing way over the course of the last few years, and it will continue doing so regardless of the political winds of change. Therefore, I think that it's less a political question, but more of a regulatory question and a compliance question. The Paris Agreement was signed many, many years ago, and humanity is theoretically on a journey to reach net zero by 2050. Practically, it's pretty hard to find geographies in which taxation is actually applied, in which corporates are actually compelled to remove what they had emitted. And this is a huge gap. The regulator should have acted long ago, and governments should have supported the gradual adoption of removal into the different sectors and industries. We do see some sectors that are more advanced, like the aviation sector, and we have some sectors that are somewhat laggards, but are making very big moves right now, like oil and gas, shipping, and that are making very impressive moves. And I'm a big believer that these moves will make a very big impact in the upcoming 2 years. I'm actually optimistic, and I'm seeing it happening regardless of the lack of compliance and regulation.
Okay.
It's happening because corporates are acting responsibly and are understanding that there's doesn't necessarily make sense to wait around for compliance, taxation, and regulation to happen. And if you kind of look at the curve of growth of high durability CDR, if you
Hmm.
drop in CDR FYI's website, you can clearly see that 2024 was a transformational year where we transitioned from 10K, 20K offtakes all the way to 300K, 500K offtakes. Q3 and Q4 were fascinating. And we saw a big leap. And we're seeing less offtakes in quantity, less transactions, but massive transactions. So when something happens, it's big, which is a signal to a market that is not experimenting anymore, but had identified where the potential is and is transacting in multi-year offtakes in very large volumes and also in sustainable price points that actually make sense and are scalable.
And I'm glad you brought up the issue of price points, because if you think about offsets, if I go to buy a plane ticket, for example, and I say I want to offset my carbon, the cost of that is 3 or 4 or 5 euro. And so that the cost of carbon offsets scales from that all the way up to, if you look at some of the direct air capture, for example, they're typically over €1,000 per ton. Where does Gigablue fit in that kind of scale in terms of cost of CO2?
So Gigablue fits in at about a third of the current market value of a high durability carbon credit. And that is primarily because of the sequestration cost that I covered earlier, that is based on gravity. The whole solution, gravity, sunlight, and water, are pretty cost effective resources.
Mhm.
And that leaves you with the cost of the substrate itself. And therefore, we can offer a price point that is around a ballpark number of a third of the price point in the market, of the high durability price point in the market. That's not to say that everything is perfect. Most corporates are still buying low permanence, and most of the portfolio of most corporates is still on the low permanence type of credits. Nature-based solutions are still most of the trade that we see in the market. And high durability is scaling up and scaling up fast. But I would like to see more of that. The transition from low permanence to high permanence should have happened faster. And if we see regulations like the ones that have been legislated in Europe and the United States that basically put a low bar of 200 years or more on a qualified carbon credit, those regulations are kicking in 2028. By that time, you should have enough supply. In order to have enough supply for corporates to be able to comply with a 200 years or more durability limit, you need to scale up high durability production now. In order to scale up production, you need demand now. And therefore, I'm calling corporates to follow the hop that we saw in 2024 and to basically ramp up offtake and demand to the 6-digit scale and continue that trend, because the CDR market will not emerge in a day. It needs to be gradually built between today and 27, 28, where compliance actually kicks in and demand increases as a result.
Okay. And what do you say to people who say that carbon offsets are licenses to pollute, or they're like mopping the floor while the tap is still running?
I'm not saying, I'm asking them to take a look at the graph of emissions over the course of the last 4 decades and tell me how successful us humans have been in avoiding emissions.
Mhm.
I'm a data driven person. I'm all into avoidance. And I think that avoidance is the way to go. But I am challenging the order in which things will be done. And as a data-driven person, we are not doing such a great job in avoiding or reducing emissions, only increasing. They always have been. They still are. And if we kind of zoom in on attempts to make a big move into avoidance, take sustainable aviation fuel, 2025 was a milestone that the whole industry has been working towards for more than 2 decades. And sustainable aviation fuel was supposed to basically cover and reach a scale of a third of the supply that the aviation market needs. Today, it is 0.53% of what the aviation market needs. So I just think that realistically, we already have removal technologies, methodologies, suppliers that are ready to scale up or have or are scaling up as we speak. And I believe that removal will be first and will gradually decrease. And so if we kind of sum it up, what I'm saying is we need to be data-driven decision makers, and we need to act today with what we have, not with what we hope to have 3 or 4 decades from today.
And if you had one message to share with policymakers or business leaders dragging their feet on CDR, what would it be?
We are trying to scale up removal and reach net zero 10 times faster than we scaled up emissions. Understanding and trying to encompass this challenge means that compliance, regulation needs to kick in yesterday. And it is a condition for the existence and survivability of the CDR market. We won't have a second chance. We have already lost one CDR era in the 90s and the early 2000s. And we now see a mature, reliable, verifiable set of technologies and suppliers that are ready to go. And what they need is demand. And the key to demand is in the hands of the regulators, and compliance needs to happen now. And the transition from VCM to the compliance market will be rapid, and it needs to happen today.
Okay.
One more note from my side.
Sure.
I've heard a regulator on stage saying that at this point, they're not financially supporting CDR because it is the business of VCs. Venture capitalists cannot support a planetary scale operation. That's not what they do. The countries and massive budgets need to be applied today in order to make an impact on climate change. And the time to act is now.
Fair enough. Left field question for you, Ori. If you could have any person or character, alive or dead, real or fictional, as a champion for CDR, who would it be and why?
Good one. I think that my champion are my 2 daughters, because they need to stay around here after I'm gone. So I think that each and every one of us can look into the next generation and basically find motivation.
Okay, we're coming towards the end of the podcast now, Ori. Is there any question I haven't asked that you wish I had, or any aspect of this we haven't touched on that you think it's important for people to be aware of?
I really enjoyed talking to you today, and there's nothing that I think that we have missed. And I'm happy to drop by again, maybe a year from now, and tell you how we did.
I look forward to it. Great. Ori, if people would like to know more about anything we talked about in the podcast today, where would you have me direct them?
I would direct them to, if they're into the scientific portion, we have a very strong scientific backbone, academic institutions, NIWA, Cochrane. There's a lot of scientific work that they can dive into and that we may make accessible. And I think that if they are more into understanding CDR and MCDR specifically, I would send them to basically start with the websites and some YouTube videos, because every CDR supplier is very transparent with everything that we do. We have a mission. I'm not talking about Gigablue alone. Every CDR supplier is on a mission, and it is an industry that is pretty visible and pretty fascinating because it combines nature and, in our case, vessels in the open ocean with dolphins on the way to do what we do. So it's a pretty interesting thing to basically watch and immerse yourself into.
Lovely. Lovely. Great. Okay, Ori, that's been fascinating. Thanks a million for coming on the podcast today.
Thank you very much. Had a great time.